Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Amini Mkize. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Remember, learners, you can interact with us via WhatsApp. Please make sure that you don't send voice notes, the videos, but you can only, type, and then we will be able to, to attend to your questions. The number is 063-629-3655. All right, grade 12 learners, we are about to actually, we've started with your final examinations, right? Yesterday you were writing CAT. So on the 11th of November, you'll be writing your physical sciences paper 1. So today we are going to focus on one of the topics when it comes to your paper 1. So we're going to focus on electrodynamics. Right. So remember, learners, electrodynamics. Right, grade 12's electrodynamics is what we are going to focus on today. Remember, your electrodynamics falls under knowledge area electricity and magnetism, which is 55 marks when it comes to your paper 1. So electrodynamics is plus or minus 15 marks, all right? Then when it comes to your examination guidelines, so you are familiar with this, learners, all right? This is what you need to know under electrodynamics, learners, right? State the energy conversion in generators, you must know that. Use the principle of electromagnetic induction to explain how a generator works. Explain the functions of the components of an AC and a DC generator. State examples of the uses of AC and DC generators. State the energy conversion in motors. Use the motor effect to explain how a motor works. Explain the functions of the components of the motor. State examples of the use of of motors. So this is what you need to know under your electrodynamics. And another thing that you need to know under alternating current. State the advantages of alternating current over direct current. Sketch graphs of voltage versus time and current versus time for an AC circuit. Define the term root mean square of an alternating voltage or current. So this is very, very important, learners. You see this definition, right? This one, the root mean square potential difference is the AC potential difference which dissipates the same amount of energy as an equivalent DC potential difference. So you should know what is a root mean square voltage or root mean square potential difference. Then the root mean square current is the alternating current which dissipates the same amount of energy as an equivalent direct current. And then solve problems using these equations. Learners, we are aware of these equations, and there's no need for you to memorize them. They're there when it comes to your data sheet. All right. Solve problems using these equations also. All right. So they are there also, these equations, when it comes to your data sheet. So there's no need to memorize them, learners. All right. Then let me just remind you, because this lesson, learners, is not actually about reteaching, electrodynamics, but we are going to focus more on exam type questions. But before we do that, learners, I think it's very, very important to, to remind you, learners, about, what is happening when it comes to generators, and what is happening, or important things when it comes to generators, and important things when it comes to motors, right? So remember, learners, a generator, it generates electricity, all right? So a generator, when it comes to energy conversion, because you'll get such questions, learners, right? So a generator converts mechanical energy to electrical energy. So I've seen in most cases, learners losing this mark, all right? Sometimes this is out of 1 mark or 2 marks, but sometimes learners, actually, they lose this mark. Reason is because they confuse, a galvanic cell, which is in paper 2, with, a generator, which is your when it comes to your paper 1. So learners, here there's no chemical energy. Chemical energy is in paper 2. So here we talk of mechanical energy. So please be careful when it comes to that, learners. All right. So for paper 1, we talk of mechanical energy. Then for paper 2, we talk of chemical energy. So please, learners, do not confuse a galvanic cell energy conversion when it comes to a galvanic cell and the energy conversion when it comes to a generator. So here we are talking about a generator, learners. So a generator converts mechanical, not chemical. So it converts mechanical energy to electrical energy, learners. So you can't lose that mark, right? And generators, they're based on which principle? They're based on electromagnetic induction. So remember, when you talk of electromagnetic induction, right? Remember, EMF is induced in a coil if there's relative movement between the coil and the magnetic field. So when the coil rotates through the magnetic field, EMF will be induced in that coil. So that is electromagnetic induction. So that is how generators work. Whether it is an AC generator or a DC generator, but they are based on the same principle, which is electromagnetic induction. And electromagnetic induction, when you explain, right, remember, induced EMF, it's EMF is induced in a coil when there's that relative movement or motion between the coil and the magnetic field. So there are 2 types of generators. We are all aware of that, which is your AC generator, which is alternating current generator, and your DC generator or direct current generator. All right. Then remember, generators, we say they generate electricity. So there it is about induced EMF, and we've explained how EMF is induced in a coil. As long as there's that relative motion between the coil and the magnetic field, EMF will be induced. So that is your electromagnetic induction. So to find the direction of the induced current, we use Fleming's right hand rule. We use Fleming's right hand rule. So you use your right hand, all right? So when it comes to your right hand, how many fingers do we have there, or do we use actually? There are 3, right? Where your thumb is always in the direction of the force, whether the coil will move up or down, all right? And then the index finger, right? It is always in the direction of of the magnetic field. So wherever your index finger is pointing, actually should point what? South pole, because when it comes to the direction of the magnetic field, right, it's always from north to what? To south. Then the middle finger is always in the direction of the current, whether the current is in or what, or out. All right. So we use Fleming's right hand rule to find the direction of the induced current when it comes to what? Generators. All right. Then another thing which is important here, learners, right? So this is a generator. All right. So what type of a generator is this one? This is an AC watt generator. Why am I saying this is an AC generator? Is because what am I having? I'm having what? I'm having what? Slip rings. Right. I'm having what? These are what? These are the slip rings. Okay. Right. So why am I saying it's a what? An AC generator? It's because of those what? Slip rings. So these are slip rings. And another thing which is important, learners, right, is to know the function of the slip rings. All right. So the slip rings, when it comes to a generator, right, slip rings, they ensure that the current. They ensure that the current in the external what? Circuit changes direction after each half turn. Right, so that is the function of what? Of the slip rings when it comes to what? An AC watt generator. And what are you also having here? You are having brushes there. This is a brush, so there are two brushes there. So the function of a carbon brush or a brush when it comes to what? A generator, whether it is AC or DC, right? So a brush, it makes contact with what? With the slip rings to ensure that the current in the external circuit, to ensure that the current also reaches what? The external what? Circuit. All right. So that is the function of the brush, right? So it makes contact with the slip rings to ensure that current reaches external circuit. Okay, so you have what? The slip rings, right? So the slip rings, they ensure that the current in the external circuit changes direction after each half turn. And then what about the brushes, right? So the brushes, they make contact with what? With the slip rings to ensure that the current that is induced in a coil, right, also reaches what? The external what? Circuit. All right. So that is the function of what? Of the brushes. Okay. So you should know that, learners. And then we're having the magnets there. Obviously, they produce what? The magnetic field. Right. So that is the function of those magnets. Okay. So they produce what? The magnetic field. And then what about the coil? The coil obviously rotates, okay, through that magnetic field. Okay. So, but there are two components that are very, very important here, which is your slip rings, right, and also your brushes. So the function of the slip rings, learners, you must know it. The function of the slip rings when it comes to a generator is to ensure that the current in the external circuit, right, changes what? Direction after each what? Half turn. What about the brushes? They make contact with what? With the slip rings to ensure that the current that is induced in the coil also reaches what? The external what? The external circuit, right? So let's go back to the position of the coil. Remember, generators, it's about, you know, induced what? Induced EMF. All right. So we have explained how EMF is induced in what? In a coil. Right. So now let's talk about the position of the coil. So the position of the coil determines whether the induced EMF will be maximum or minimum. All right. So the position of the coil determines whether the induced EMF will be maximum or what? Or minimum. For example, in this case, So let's check this diagram alongside. The coil, you can see, is in the horizontal what position. All right. So if the coil is in the horizontal position as shown in the diagram alongside, you should know that maximum EMF or maximum current is induced in that coil. All right. So it's what we need to know. If the coil is in the horizontal position as shown in the diagram there, you can see the diagram alongside. You should know that the EMF that is induced in that coil would be what? Will be maximum. So, and again, you need to know why maximum EMF is what is induced. Okay, maximum EMF is induced because the normal to the plane, right, is parallel to what? To the magnetic field. And if the normal to the plane is parallel to the magnetic field, right, magnetic magnetic flux, or the angle when it comes to this equation, right, which is your what BA what cos theta. All right, so the angle here will be what? Will be maximum. Sorry, not the maximum, but the angle will be what? Will be 0. Then you have BA cos what here? Cos 0 degrees. All right. So if the normal to the plane is parallel to the magnetic field, okay, so the angle between the normal and the magnetic field will be 0 degrees, and then your magnetic flux will be what? Will be the maximum. All right. So if the coil is in the horizontal position, maximum EMF or maximum current is what is induced. Why maximum current is induced is because normal to the plane is parallel to the magnetic field. And if normal to the plane is parallel to the magnetic field, theta, which is the angle between the normal and the magnetic field, will be 0 degrees. Then magnetic flux will also be what? The maximum. So which means that if the coil actually is in the horizontal position, there will be change in what? In magnetic flux. All right. So if there's change in magnetic flux, then there will be what? EMF that will be induced in that coil, and the EMF that will be induced in that coil will be what? The maximum. So that is very, very important, learners. So know that if the coil is in the horizontal position, maximum EMF is what is induced. Why maximum EMF is induced? So when you explain, you need to talk about the what? The normal to the plane. Remember, if we talk of the normal, we are talking about what? The line that is drawn perpendicular to that to the coil. So the line that is drawn perpendicular. So I'm drawing this line perpendicular to the coil, right? And then this is the magnetic field, right? So this is the magnetic field. So you can see that the normal to the plane is parallel to what? To the magnetic field. So if the normal to the plane is parallel to the magnetic field, then a magnetic flux will be what? Will be the maximum. So that is very, very important, learners. All right. But note this, learners. Remember, it is the normal to the plane that is parallel to the magnetic field, but the coil is perpendicular to what? To the magnetic field. All right. So if these are what? Magnetic field lines. So check here. This is the coil. You'll see that the coil here is what? It's perpendicular to what? To the magnetic field. So the normal to the plane, it is what? Parallel to the magnetic field, right? Therefore, magnetic flux will be what? Will be the maximum. And if the magnetic flux is the maximum, right, EMF is also going to be what? The maximum, right? But the coil is perpendicular to the magnetic field. All right. So please be careful when they ask questions. Are they talking about what? The normal to the plane or the coil? So the normal to the plane is parallel to the magnetic field, but the coil is perpendicular to what? To the magnetic field. But when you explain, you need to talk about the normal to the plane. All right. So the normal to the plane will be parallel to the magnetic field, and if the normal to the plane is parallel to the magnetic field, then magnetic flux will be the maximum, and if the magnetic flux is the maximum, therefore EMF is also going to be what? The maximum. All right. So I've talked about an AC generator. Why am I saying this an AC generator? Is because of the slip rings. So what is the function of the slip rings? Is to ensure that the current in the external circuit changes direction after each half turn. We have talked about the function of what of the brushes. They make contact, all right, with the slip rings to ensure that the current also reaches what? The external circuit. All right. So that is an AC watt generator. So the position of the coil, vertical position now, right? So if the coil is in the vertical position, you should know that minimum EMF or zero EMF is what is induced. Or if the EMF is the minimum, also the current is also what the minimum. All right. So why minimum EMF is induced if the coil is in the vertical position as shown in the diagram, right? Is because the normal to the plane is perpendicular to what? To the magnetic field, right? So if the normal to the plane is perpendicular to the magnetic field, right, theta, which is the angle between the normal and the magnetic field, will be 90 degrees. And cos of 90 degrees, we know is 0, right? So that is how actually you have to explain. Normal to the plane, right? It is what? Perpendicular to what? To the magnetic field. And if the normal to the to the plane of the coil is perpendicular to the magnetic field, right? Magnetic flux will be 0, right? And if magnetic flux is 0, therefore, what EMF is also going to be 0 what? 0 volts. All right. So if the coil is in the vertical position, 0 EMF is induced. But if the coil is in the horizontal position, maximum EMF is what? Is induced. So to explain, you can even just talk about what? Change in magnetic flux. So if the coil is in the horizontal position, there will be change in what? In magnetic flux. All right. But if the coil is in the vertical position, there will be no change in what? In magnetic flux. So no change in magnetic flux. Then what about EMF? EMF is also going to be what? 0 volts. So that is very, very important, learners. All right. Then this is the graph of EMF, the induced EMF, right? The induced EMF versus position of the coil for an AC generator. AC generator, remember, current in the external circuit alternates. Why? Because of the slip rings. All right. So check here. This is when you draw this graph, learners, please be careful. Make sure that you label your axis, right? So here, this side, we're having what? The induced what? EMF. And you also need to include the units. So the induced EMF in what? In volts. And then this side, we're having the position. But in most cases, it's time, right? Then time in what? In seconds. All right. So please make sure that you label your axis, right? Your dependent variable and also your independent variable. So if you look at position 1, this is the position of the coil. You can see the coil is in the vertical position. We have talked about that already. That if the coil is in the vertical position as shown there, right? 0 EMF is what is induced. That is why our graph starts from what? From 0. Check here. The coil is in the horizontal position. All right. So if the coil is in the horizontal position, maximum EMF is what? Is induced. So there we are having what? Maximum what? Potential difference or maximum what? EMF. So let's go to position 3. The coil is in the vertical what? Position. So if the coil is in the vertical position, 0 EMF is what? Is induced. Check position 4, horizontal position. Maximum what? EMF. But now it is maximum EMF in the opposite what? Direction. Because remember, when it comes to a generator, there are slip rings, right? And the function of the slip rings is to ensure that the current in the external circuit changes direction after each half what? 10. So this is half 10. Then after each half 10, the direction of the induced EMF what? Changes. So there you are having what? Maximum what? EMF. So this is maximum EMF, but maximum EMF in the opposite what now? Direction. So please be careful, learners, when you draw these graphs, right? So check whether we are drawing the graph of EMF versus time for an AC generator or for what? For a DC what? Generator. For an AC, current alternates, all right? Because of the slip rings, right? Then check also the position. Is the coil in the horizontal position? Is the coil in the vertical position? So horizontal position, maximum EMF. Vertical position, 0 what? 0 EMF. So please be careful when it comes to that, learners. So you must be able to draw these graphs. Then a DC generator, right? What makes a generator to be a DC, right? We know it is what? The split ring what commutators. All right. So there's a split. Actually, it's a split ring commutator. All right. So you can just say it's a split ring, right? Or a split ring what commutator. So this is a split ring commutator. All right. That what makes a generator to be what? To be a DC what generator. And what is the function of this split ring commutator? Is to ensure that the current in the external circuit does not change what? Direction. Is to ensure that the current flows in one direction, right? That is the function of what? Of a split ring commutator, is to ensure that the current in the external what? Circuit flows in one direction. Remember, when it comes to your AC generator, current alternates because of the slip rings, right? So current changes direction after each half turn. But when it comes to this one, there is a split ring commutator. What is the function of that component? The function of that component is to ensure that the current in the external circuit flows in what? In one direction. So that is very, very important, learners. Then the carbon brushes, same function, right, as in an AC generator. They make contact with the split ring commutator to ensure that the current also reaches what? The external what? Circuit. But please, let's not confuse, the functions. For a split ring, split ring commutator is to ensure that the current in the external circuit flows in what? In one direction. But when it comes to an AC generator, right, the current alternates because of what? Of the split ring what? Commutators, right? And another thing that you need to be careful about, learners, all right? Let me just let me use this diagram, right? The difference when it comes to these two types of generators is in the external circuit, all right? The difference is in the external what? Circuit, all right? Remember, when it comes to an AC generator, there is a split. Sorry, there are slip rings, right? So slip rings, they ensure that the current changes direction after each half turn. All right. So the current changes direction in the external circuit when it comes to what? An AC generator. But when it comes to a DC generator, current does not change what? Direction. So the difference is in the external what? Circuit, right? Because of those two components. Current changes direction when it comes to an AC generator, but when it comes to what? A DC generator, current flows in one direction. But when it comes to the internal circuit, current in a coil, right? Current in a coil alternates, all right? Current in a coil alternates, whether it is an AC generator or a DC what? Generator. So current in a coil changes direction. The difference is in the external what? Circuit, all right? So current in a coil changes direction, whether it is an AC generator or what? Or a DC what? Generator. Because the reason why I'm saying that, let me just do this. The reason why I'm saying that, it's because, let me just erase this. Right. The reason why I'm saying that, so check here, because of the shape of the coil, if the current this side is in, right, this side, it will be what? Out. So DC current is in, right? VA current should be what? Should be out. All right. So even when it comes to your DC generator, this is how the coil is, right? So which means that when the current is in this side, on the other side the current will be what? Will be out. So current in a coil, whether it is AC or DC generator, it alternates. But when it comes to the external circuit, when it comes to an AC, it changes direction. But when it comes to a DC, current does not change direction, or current flows in what? In one direction. All right. So let's move on. So for a DC generator, because of the split ring commutator, right? Because of the split ring commutator, current flows in what? In one direction. So the position of the coil here, we all know now that the coil is in the vertical position. So it's vertical position, horizontal position, maximum what? EMF. And then, so it's vertical position, horizontal position, vertical what? Position. Because of the split ring, right? Then the current won't change what? Direction. All right. Then you have horizontal position, maximum EMF, and then vertical position, and here we are going to have what? Minimum what? EMF. All right. So you can see the difference between the two graphs. All right. You can see the difference between the two graphs. For the AC current alternates, it changes direction, but for a DC generator, the induced current does not change direction, or the induced EMF does not change what? Does not change direction. So please be careful when they say draw this graph. So check whether this is AC or what? Or DC. All right. So AC current alternates, EMF alternates, right? After each half turn, right? DC current does not change direction. EMF also does not change what? Direction. So please be careful when it comes to that. So you can see here vertical right. Position 1, vertical what? Position 0 EMF is induced. Horizontal position, maximum EMF, you can see there we're having maximum, right? And then position 3 here, vertical position, you have what there? 0 EMF, horizontal position, maximum EMF, vertical position, which is this one, then we have what? 0 EMF there. So you can see the current is in the same what direction, or the potential difference here is in the same what direction. Because even if you can draw the graph of current versus time, so it will be same shape, same shape, but remember there now we are having current, it's versus time. So there we are going to have what? I max instead of what? Of V max. All right, but the shape of the graphs is the same, whether it is EMF versus time or what current versus time for a DC what generator. All right. Then how can the amount of the EMF or current be increased when it comes to a generator, whether it is AC or DC generator? Remember, we can increase the amount of EMF that is induced in a coil, or the amount of current that is induced in a coil, by increasing the number of turns, or you can say by increasing the number of coins, or sorry, not coins, but of coils, or what, or windings. All right, that is how actually we can increase the amount of EMF induced in what? In a coil. Then we can also use what? A stronger magnet. Please be careful, learners, here, right? This, when it comes to A, this only affects what? The amount of EMF induced in what? In a coil. All right. So if, for example, you're having a graph, right? You're having what? Potential difference versus time. And let's say this is your graph for what? Maybe for what? An AC generator. The EMF induced when it comes to what? An AC generator. So if you increase the number of turns, right? If you increase the number of turns, then what will be affected is only the amount of EMF that will be what? That is induced in that coil. So the amount of EMF induced will what? Will increase. So you will have something like this. So the EMF induced will be more than before. All right. Same even for number what? For number B, right? The only thing that will be affected is what? Is the induced what? EMF. So, but please be careful now when it comes to number C, right? So when it comes to C, increasing the speed of rotation of the coil, right? So if we increase the speed of rotation of the coil, EMF induced in that coil will increase. But there are two things that will increase. That will be affected actually. It's not only the amount of EMF induced in a coil. So let's say we're having this. All right. Then maybe here we're having 0.1, and then there we're having what? 0.2. This is time in what? In seconds. And then this is potential difference in what? In volts. So there we're having what? Maximum what? EMF. All right. So let's say the speed of rotation of the coil is doubled, right? So we have doubled the speed, right? So if the speed of rotation of the coil is doubled, how will the EMF be affected? The EMF will also be what? Will be doubled. All right. So for that, I need a different color here so that you'll see what I'm talking about. Right. So the maximum, sorry, the EMF induced in a coil will be what? Will be doubled. Right. But there's another thing that will be affected. Right. So according to the equation, V equals to F what? F lambda. Right. So if the speed of rotation of the coil is doubled, the frequency is also going to be what? Is also going to be doubled. All right. Remember, what is the frequency? The frequency, that is the total number of waves passing a point per watt per second. All right. So if this is doubled, this is also going to be what? Doubled. But what about period? Period is, remember, is given by 1 over what? Over F. So if frequency is doubled, it means that period will be what? Will be halved. I hope we are using those equations. You can see what I'm talking about. All right. So if the frequency, the speed of rotation of the coil is doubled, frequency is also going to be what? Is going to be doubled. Then what about period? Period will be what? Will be halved. So then when you draw this graph, all right. Let me use a black ink there. Right. So we are saying this will be what? Will be doubled. So the total number of waves passing a point here will be more than what before. So let me just do this. So this is what you are going to have. Right? So total number of waves passing this was 0.1 is what it was half, but now it's what it's a full wave. All right. So please be careful, learners, when it comes to that. That when the speed of rotation of the coil is doubled, there are two things that will be affected. All right. So there are two things that will be affected. All right. So one, it is the EMF that is induced, or the current that is being what induced. All right. Then another thing that will be affected is what is the frequency. And if the frequency is affected, how is the frequency affected? If the speed is doubled, frequency is also doubled. But what about the period? Period is what is half. For example, here, right? What half of 0.1, right? Then you can get that. I hope you can see what I'm talking about here. So there are two things that are being affected here. It's what is the maximum, what actually is the EMF induced, and also what the frequency. All right. And if the frequency is affected, also, you know, the period will be what will be affected. But when it comes to A and B, right, the only thing that is being affected there is the induced EMF, right? But when it comes to C, it should be induced EMF and what? And the frequency. And if the frequency is, if the speed is doubled, the frequency is also going to be what? It's also going to be doubled. Then what about the period? The period will be what? Halved. So please be careful when it comes to that. So this is just the summary of generators. All right. So we have talked about this already. Motors, they convert, you know, electrical energy to mechanical energy, and then they're based on motor effect. All right. There are two types of motors. We all aware of that. All right. An AC motor and a DC what motor. Then remember, motors is about rotation of the coil, but when it comes to generators, it's about induced EMF. That is why we talk about things that we can do to increase the amount of EMF induced in a coil. All right. Then here it's about rotation, okay, of the coil. And to find the direction of rotation of the coil, we use Fleming's what left-hand rule. So please be careful when it comes to that. So this is a DC motor. This is just an example of a DC motor. You'll see there's the source of power there. Because remember, motors, they convert electrical energy to what? To mechanical what? Energy. So we need a source of power there, right? And this is a DC. Why DC? The reason why this one is DC is because of the split ring commutator. So, but please be careful, learners. The function of a split ring commutator when it comes to a generator is to ensure that the current in the external circuit flows in one direction. But what is the function of the split ring commutator when it comes to a motor? Is to ensure that the coil rotates in one direction. Coil rotates in what? In one direction. Coil rotates in one direction. That is, remember, here it's about rotation. So what is the function of a split ring commutator? Is to ensure that the coil rotates in one direction. So please do not confuse the two, right? So split ring commutator, when it comes to a DC motor, the function of it is to ensure that the coil rotates in what? In one direction. Carbon brushes, they make contact with what? With the split rings. So, yes, the split ring commutator, to ensure that the current that is in the external circuit also reaches what? The internal circuit. Because now remember, the current now is coming from the external circuit. Remember, there's a source of power, all right? So the carbon brushes, they make contact with what? With the split ring commutator to ensure that the current also flows in the internal what now? Circuit. But when it comes to, you know, a generator, the brushes, they make contact with what? With either the split ring commutator or slip rings to ensure that the current also reaches the external circuit. Remember, the current is coming from the internal circuit. So it's from internal to external. But when it comes to this, which is what now? The motors, the current is from the external to the internal. So they are making that contact, that electrical contact between what? The internal circuit and the external what? Circuit. So that is the function of the carbon brushes, all right? Then please, learners, a split ring commutator, it ensures that the coil rotates in one direction when it comes to what? Motors. All right, so motors is about rotation. All right, so and the coil will either rotate clockwise or what? Or anti-clockwise. To find that, we use Fleming's left-hand rule. So using Fleming's left-hand rule, the thumb is in the direction of the force, whether the coil will move up or down. The index finger is in the direction of the magnetic field. Wherever this finger is pointing, you should point south pole, because the direction of the magnetic field is always from north to what? To south. The middle finger is always in the direction of the current, whether the current is in or what or out. This is an AC motor, learners. AC motor, why am I saying it's an AC motor? You can see that there's a source of power, right? Okay, then there are slip rings. What is the function of the slip rings? Coil here should rotate in opposite what? Directions. In opposite directions. Right, so please let us be careful. The function of a slip ring when it comes to a generator is different to the function of a slip ring when it comes to what? A motor. Motor is about rotation. So the function of this slip ring slip rings when it comes to motors is to ensure that the coil rotate in opposite what? Direction. So please be careful, learners. How can we increase the efficiency of a motor, right? We can use a stronger magnet, we can increase the number of turns, we can increase power, or we can use the source of power with high potential what? Difference. That is how actually we can increase the efficiency of what? Of a motor, whether it is AC or what? Or DC. But please be careful. Motors is about rotation, and then generators is about what? Induced what? EMF or induced what? Current. And those graphs, the graph of EMF versus time, the graph of current versus time, are for generators. We don't have graphs when it comes to what? Motors. All right. So those graphs are for what? Are for generators. The amount of EMF induced, or the amount of current that is induced in a coil when it comes to those generators. All right. Then this is just the summary, right? Okay, we have talked to this already. Then summary of both machines, generator, motor. All right, so we have talked about this already. Then advantages of using AC. So power stations, they prefer to use AC voltage rather than using DC watt voltage. So you should know why they prefer to use that. It's because AC voltage can be stepped up or down using transformers. AC can be transmitted over long distances at high voltage and low current to minimize energy loss due to what? Due to heat. So these two, they are very, very important. So the third one, if I don't think so, I don't think if they will ask you more than two. So in most cases, it's only one function, right? Or the one advantage of using AC over what? Over DC. So use the first two. The third one, don't. All right. So if they're asking you about the advantages, or one advantage of using AC over DC, talk about the first one or talk about the second one. Leave the third one. All right. Then alternating current. This is your data sheet, learners. So we have seen learners using incorrect equations when it comes to electrodynamics. For example, if you check this equation, right, it's different from this one, learners. It's not the same, although we are going to get the same answer. But for what? Electrodynamics, we use equations under alternating what? Alternating what? Current. Those equations are for electrodynamics. Those equations are for question 9 when it comes to your paper 1, because your electrodynamics is question what? Question 9. So these equations are for you, are for question 9, or are for what? Electrodynamics. So if you are going to use this equation instead of using this one, you will be penalized for doing that, because we can't say because the answers are the same, then let's give learners marks. We can't do that, because you are given those equations. All right. So those equations that are there, right, when it comes to your data sheet, learners. So please use the correct the correct equations. All right. Then again, please be careful when it comes to these learners. We'll find learners writing P average equals to I squared RMS. RMS. We don't have that. We don't have root mean square resistance, right? Resistance is just resistance. We don't have maximum resistance and root mean square resistance. Resistance is just what? Resistance. So copy the equations as they are on your formula sheet, learners. All right, and you will be given that formula sheet, so you know that. All right. Then these are the equations where we know VRMS is root mean square voltage, Vmax is maximum voltage, or sometimes it's called peak voltage. IRMS is the root mean square current, Imax, that is your what, your maximum what, your maximum current, average power. All right, so we all know that. Okay, then you will also get multiple choice questions, learners. We are aware of that. There will be multiple choice questions. Your question 1, right, out of 20 marks, right, out of that 20 marks, 2 marks are for electrodynamics. All right, so you will get a question on electrodynamics or a multiple choice question on what, on electrodynamics. Right, so let's look at this one, learners. The sketch below represents an alternating current what generator. You are told that this is what, a generator, right? So a generator converts what mechanical energy to electrical energy. And why are they saying it's an AC generator? It's because of what? You can see there we're having what, the slip rings. What is the function of it? The slip ring or slip rings, they ensure that the current in the external circuit changes direction after each what, half turn. So that is very, very important. All right. So, and this is the generator. It is based on which principle? Electromagnetic what? Induction. So those are the things that you need to know. All right. Then there are also carbon brushes here. Why are they there? They maintain that electrical contact between the internal and the external circuit. So those are the things that you need to know. All right. Which one of the following is correct about an AC generator? This is a generator. We know. One, they're talking about what? The energy conversion, right? So if it's energy conversion, we know very well that it should be mechanical, not chemical, right? Mechanical to electrical what? Energy, right? So if you check A, it's mechanical, so I can tick there. But when it comes to B, it's electrical, it can be. When it comes to C, it also can be because it's electrical. When it comes to D, it's mechanical to what? To electrical. Type of ring used. This is an AC generator. So the type of ring used, we all know is what? It's a slip ring, right? So slip rings, it can be a slip ring commutator. Slip rings here, it can be what? A slip ring what? Commutator. So where there are 2 ticks, that will be our correct what? Correct answer. So the correct answer here will be what? Will be A. So you must know your story, right? Under generators and also under what? Under motors. All right, I hope we're still together. Then the device that uses electrical energy to produce mechanical energy. So can you see the energy conversion here, learners? It's electrical to what? To mechanical. And an electrical machine that converts electrical energy to what? To mechanical energy to what? It's a motor. So we can't, it's a dynamo, no. An alternator, no. This is a generator, it can't be a generator, it should be what? An electrical what? Electrical motor. So these are the questions. So they're not difficult, those questions, you know, or those multiple choice questions from what? From electrodynamics. All right. Then this one, please be careful when it comes to this one, learners. All right. A DC generator. This is the generator. Okay, it's a DC generator. It's a generator energy conversion. I know the energy conversion is from mechanical to electrical. Based on which principle? Electromagnetic what? Induction. It's a DC. So what makes it to be a DC? It's a split ring what? Commutator. What is the split ring commutator? What it does, it ensures that the current flows in what? In one direction in the external what? Circuit. Okay, fine. What are they looking for here? A DC generator functions at a frequency of 80 Hertz. What is the meaning of 80 Hertz, right? Remember, 80 Hertz, that is frequency, all right? And frequency is the total number of waves passing a point per second. So if you have 80 Hertz, this is the same as 80 watt per second. So there are 80 waves. There are 80 full waves passing a point per second, all right? So that is the meaning of 80 Hertz. So the 80 waves per second. 80 waves per what? Per second. All right. So a DC generator functions at a frequency of 80 Hertz. All right. The number of times, right, the output voltage reaches the maximum in 1 second, right? Reaches the maximum in what? In 1 second. The output. So here, let me just draw the graph. And this should be the graph of output voltage versus time for which generator? A DC generator. So I'm having something like this, right? So this is the output voltage, all right? And the number of times the output voltage reaches the maximum. So this is the maximum. So in one wave, because this is half of a wave, this is another half of a wave, right? So 2 halves, that makes 1 wave, right? So in 1 wave, how many maximum voltages are you having? Or how many times the output voltage reaches the maximum? twice. You can see that 1, 2. So this is one wave. So in one wave, how many times the output voltage reaches the maximum? Twice. Okay? So in one wave is what? Is twice. Then how many waves are we having here? 80 waves. All right? So in 80 waves, you multiply that by what? By 2. So what is 80 multiplied by 2? Then we're having what? 160. So please be careful when it comes to that, learners. All right? We are having what? 160. So in one wave, right, you are having how many maximum voltage is 1, 2, all right? Or how many times does the output voltage reaches the maximum? 1, 2. So in one wave, it reaches the maximum how many times? Twice, all right? Then in 80 waves, it will be 2 times what? Times 8. And then the answer will be what? Will be 100 and what? And 60. So I hope we are together when it comes to that, learners. All right. Then let's look at this one. The diagram shows the variation in EMF produced by a generator. So what type of a generator that can produce such a graph of EMF versus time? The graph, you can see the EMF here alternates. All right. So it changes what direction. So this should be what? An AC what? Generator. This should be what? An AC what? Generator. Okay, because you can see the EMF here changes what direction. So this is the maximum EMF in the positive direction, maximum EMF in the negative what direction. All right, then what is the question? If the armature of the generator is rotated twice the speed, right, how will the EMF and the period shown by the graph change? I said to you, there are 3 things that affect the EMF, right? Or the induced what EMF, right? If we increase the number of turns, right, the EMF induced also increases. That is the only thing that will be affected if we increase the number of turns. If we use a stronger magnet, EMF will be what will be affected, and that will be the only thing that will be affected. But if we increase the speed of rotation, 2 things will be affected. I've already talked about that. I said it is the EMF and also what? The frequency. And if the frequency is affected, what about the period? The period is also going to be what? Affected. So this is rotated twice the speed. So the speed is doubled. What about EMF? EMF is also going to be what? Doubled. So it will be more than 10, right? It will be more than what? More than 10. So it will be 20 instead of what? Of 10. Because the speed is what? Is doubled. So even there, you are going to have what? Negative what? Negative 20. But what about the frequency? The frequency is also going to be what? Doubled. So number of waves passing a point in 0.1 is half. Instead of half, now we're going to have what? A full wave. All right? So this is what you are going to have. So that. Then this is what we are going to have, right? Let me draw it nicely. Okay. So this is what we are going to have. Okay. So let's check here. You have what? The EMF will be affected. It will be more than 10. All right. The frequency will be doubled. Okay. Total number of waves passing a point. It's more than half now. It's one wave. All right. Then what about the period? Okay. The period of this wave was 0.2 because you know what is period, learners, right? Period, that is the total time taken to complete one wave, right? So the total time taken to complete one wave is what? Is 0.2. Total time taken to complete a single cycle, you can see this is one wave, so it's 0.2. So if the frequency is doubled, period will be halved. So what is half of 0.2? Half of 0.2 will be what? 0.1. So look at the period now. It will be what? 0.1. Total time taken to complete one wave. You can see that. It's 0.1. Okay? So if the frequency is doubled, the period will be what? Will be halved. What was the period before? Total time taken to complete one wave, 0.2. Now this is halved. Divide that by 2. Then we are left with what? With 0.1. So let's check here. So the correct answer, it will be greater than what? 10. Greater than 10. It can't be equals to 10. it can't be less than 10. Then let's check the period. The period, it can't be the same. Can't be 0.2. We are expecting what? 0.1. 0.1. It can't be 0.4. So where we are having 2 ticks, then we are checking that one. So that is our correct answer. So please be careful when it comes to such questions. All right. So these are solutions. We have talked about that. This is a structured question or an exam type question, which is what you'll get when it comes to your paper 1. Your question 9 will be electrodynamics learners. All right. So the diagram given below is a schematic representation of what? Of an AC. They're asking you about what? An AC generator. So what makes this to be an AC? You know, is R. And what is R? Or is component R? And what is component R in this case? Your component R in this case will be what? Will be the slip rings. So we can label that. These are the slip rings. You are having the brushes there. And then B, you are having, we are having AB there. That represents what? The coil. And this will assist us whether the current is moving in or out, A to B or B to what? To A. So this is what an AC generator. There's a lot that they can ask here. So let's check what are they looking for this question. All right. Write down the name of the part labeled R. So already we have talked about that. Slip what? Slip rings. Okay. Function of part labeled R. What is the function of a slip ring? Is to ensure that the current in the external circuit changes direction after each half turn. Then you get your 2 marks. You get that 1 mark, it's simple. You get the second mark there, or that 2 marks, which is your 9.1.2. Then 9.2. State one principle on which an AC generator works. Generators that are based on electromagnetic induction. We are all aware of that. So can you see how easy questions are? Electromagnetic induction. All right. So the principle in which they are based on, whether it is AC or DC, is electromagnetic induction. Right. So let's check this question. And what is important, Learners, you have to read and understand what the questions. All right. For example, if you can check previously, right, or in the previous slide. Okay. Previous slide. You were given what? Sorry about that. Okay, you were given this diagram. Right? You can't just say, oh, let me just look at it and then, and then try to come up with what the name of it, whether it is an AC or a DC. Sometimes you will be like, what is important? What I'm trying to say to you, learners, is very, very important to read the statement given so that you'll understand what they are looking for or what they are talking about. All right. So that is very, very important. Don't just say, because I'm looking at the diagram, I can see there are slip rings, and then you think this is what a generator. What if it's not a generator, but it's a motor, and it was stipulated on that statement given? But you will say maybe it's a generator because you don't see what a source of power. Sometimes they won't even include that source of power. But as long as they're going to say this is a motor, so you have to take that. Okay. So that is very, very important. Let us read and understand the statement given before you answer the questions, right? Then, if the armature, which is your 9.3 now, if the armature is rotated in the direction as indicated in the diagram, right? Which way will the current flow in the armature, right? If the armature, which is the coil, another name for the coil is the armature, right, is rotated in the direction as indicated in the diagram, which way will the current flow in the armature? Is it from A to B or from B to A? And you have to choose between A to B or from what? From B to A. So for that question, you can't say yes. All right? For that question, you can't say yes. You have to choose either A to B or B to what? To A. There's no X to Y there or Y to X, but you need to choose from A to what? To B or B to what? To A. Okay. Then, so let's check. This is what, learners, this is a generator. And to find the direction of the induced current when it comes to generators, we use Fleming's right-hand rule. And if you can check on the diagram, this arrow is not just the design, all right? You see this arrow. it talks about the rotation, whether the coil rotates clockwise or what, or anti-clockwise. So the coil rotates like this, all right? So this coil rotates clockwise. So if this coil rotates clockwise, this part AB will move down, and then this side, let me just say it's CD, it will move up. So it will be down, up, and that shows what? A clockwise what? Rotation. So this coil will move down, and then this coil, part of the coil will move what? Up. All right? So it will be down, up, or up, down, just like that. All right? So that shows a clockwise what? Movement. Okay, so the focus is side AB. We can't focus on both sides, because if this side AB goes down, side CD will move up. All right? So we need to focus on one side, and the side that we need to focus on is side AB. All right? So I'm using Fleming's right. I'm using my right hand, all right? So you can't use left for what? For generators, okay? If it was a motor, we are going to use left, but this is a generator, so we have to use right, okay? So I'm doing that. So one, I just want to check whether the current will move in or out. If it's in, it's B to A. If it's out, it's A to what? To B, right? So I'm starting now. Look at my index finger, right? So my index finger is pointing south pole, because this index finger shows the direction of what? Of the magnetic field, from north to what? To south. All right. Then check if I'm like this, right? The thumb is facing up, right? And this is the direction of the force. And for AB moves down. So I need to rotate my hand to accommodate the direction of the force. All right. So when I rotate it, okay, so I've accommodated now the direction of the force. So AB moves down. The direction of the magnetic field is north to south. Then look at my middle finger. It's pointing out of the screen. All right. So since it is pointing out of the screen, it means that the current is out, which is A to what? To B. So it's supposed to be what? A to what? To B. So if it's A to B, then this side it would be what? C to D. Remember, if the current is in this side it should be what? Out. Or if it's out this side, on the other side, it should be what? In. That is very, very important. So please use the right hand, right? So in this case, it's the right hand that you need to use, or the right hand rule. Okay. Then, so here it will be what? A to what? To B. So it's A to B. You have to choose. What effect does the changing the polarity of the magnet have on the output voltage? Learners here, they are changing the polarity, right? So polarity meaning, it means that where you have north, now we are going to have south, right? Where you have south, we are going to have what? North. So they're just changing the polarity. Does the polarity affect the induced EMF or the output voltage? It doesn't. What affects the output voltage? The output voltage will be affected by what? If we are going to use what now? A magnet that is stronger than this one, it's when the output voltage will be affected. But if we just change, we are using the same magnet, but we are only changing the polarity. All right, where we have north, we have south, and then where we have south, we have north. That will not affect what? The output voltage, or that will not affect what? The induced EMF. All right, so no effect. So there will be no effect. So here, no effect, but they want us to choose. Increases, decreases, or remains the same. So the correct answer would be what? Remains what? The same, because the polarity does not affect the EMF. What affects the EMF is if instead we are using a magnet that is stronger than this one, then that is when the output voltage will be affected, right? What is the position of the coil relative to the magnetic field when the output voltage is at the minimum, right? What is the position of what? Of the coil, right? Relative to the magnetic field when the output voltage is what? Is the maximum, all right? They're asking us about the position of the coil. If we were to choose between horizontal and vertical, then this was going to be what? Vertical. If we were to choose between horizontal and what? And vertical. If we were to choose between parallel and perpendicular, Parallel and perpendicular, right? Here we are going to choose what? Parallel. Why am I saying parallel? Let's go back. They are talking about the coil relative to the magnetic field, all right? Not normal, or the normal relative to what? To the magnetic field. If it was normal relative to the magnetic field, then we're going to choose perpendicular. But it's not normal relative to the magnetic field, but it's the coil relative to the magnetic field. So coil relative to the magnetic field, then it will be what? Parallel. So let me go back to this slide because this will assist us to understand what I'm talking about. So I want this slide. Where we're talking about positions. Yeah, this one. Yes. So if a coil is in the vertical position, as shown in the diagram alongside, 0 volts or 0 amperes current is induced in a coil, right? So that is why I said to you, if they were asking about, we had to choose between vertical and horizontal. We are going to choose vertical, right? But if we had to choose between parallel and perpendicular, here, it is the normal to the plane that is perpendicular. But the coil, because they're asking us about the coil is parallel to what? To the magnetic field. So if the coil is parallel to the magnetic field, 0 EMF is induced, right? If it was the normal relative to the magnetic field, the normal to the plane, perpendicular to what? To the magnetic field. So please be careful when they ask questions, right? Check whether they're talking about what? Normal to the plane relative to the magnetic field, all right? Normal of the coil relative to the magnetic field, or coil relative to the magnetic field. So if it was normal relative to the magnetic field, then we're going to choose perpendicular. But if it is coil relative to the magnetic field, then we have to choose what? Parallel. So the correct answer here would be what? Will be parallel. So please be careful when it comes to that. Coil being parallel to the magnetic field, 0 EMF is induced. Coil being perpendicular to the magnetic field, maximum EMF is induced. But normal to the plane, perpendicular to the magnetic field, 0 EMF. Normal to the plane, parallel to the magnetic field, maximum what? EMF. So please be careful when it comes to that, learners. All right, then let's check other questions. All right, so we are choosing parallel. If we had to choose between vertical and horizontal, then it should be vertical. So let's check here, what are they looking for? Right, 9.6. The graph shows the potential difference delivered by an AC source to a light bulb which is dissipating 15 watts. All right, so 15 watts, that is average power. We talk of average power here. All right, so we have average power, and when it comes to this graph, this is an AC watt generator. So this will be produced by an AC generator because of those slip rings, right? So here, learners, we're having what here? Maximum. We have Vmax here. We have Vmax, we also have what? Average power. So when it comes to this graph, we have Vmax, you also have what? The average power, all right? Then what DC voltage would have to be supplied to keep the bulb burning at the same brightness, right? So here, remember, what is root mean square voltage, right? Root mean square voltage, it's an AC voltage that dissipates the same amount of what? Power as what? As a DC. Let me repeat that. What is the root mean square voltage? Root mean square voltage, it's an AC voltage that dissipates or produces the same amount of energy as what? As DC. So DC voltage is the same as VRMS. All right? Okay? So DC voltage is the same as what? As VRMS. So what DC voltage would have to be supplied to keep the bulb burning at the same what? At the same brightness. So they are asking us about what here? The root mean square voltage. Why am I saying root mean square voltage? Root mean square voltage is an AC voltage that dissipates the same amount of power as what? As DC voltage. So DC voltage is the same as root mean square what? Voltage. So are we given root mean square voltage here? No, we are not given the root mean square voltage, but we can calculate that. That is why there you see 3 marks there. So if you are just going to write that 17 volts, 17 volts is not the root mean square voltage or the DC voltage. It is the maximum watt voltage. But we can use that to calculate the DC voltage or the root mean square watt voltage. And where do we get the equation? From the formula sheet or from the data sheet, which is given by root mean square voltage equals to Vmax over what? Over root 2. So what is our Vmax? Is 17, and then you divide that by what? By root 2. Then you will get your answer in what? In volts. All right. So that will be our what? Root mean square what? Voltage. All right. Then what is the peak current? Peak current is also maximum. So instead of using maximum, they can say peak. Maximum voltage, peak voltage. Maximum current, peak current. All right. So they're looking for what here? Maximum what? Maximum what current. Okay. So to get the maximum current, the equation that we have to use, there is only one equation with maximum current here. You can check on your data sheet. So it's I what? Root mean square current is given by I max over what? Over root 2. Okay, so we are looking for what? Maximum. So first thing that we need to do here is to get the root mean square current. All right, so how are we going to get the root mean square current so that we can get the maximum current? We are given average power, and we also have root mean square what now? Voltage. So average power, write it correctly, is Vrms multiplied by R what? RMS. Okay, then here I'm having what? 15. And then what is the root mean square what voltage? I've calculated that. That's 17 over root 2. I multiply that by what? IRMS, right? Then my IRMS, I will get my IRMS, right? So from here, my IRMS, I will divide by what here? I will divide by 17 over what? Root 2. Divide by what? 17 over what? Over root 2. Okay? So that will be my IRMS, right? Then my IRMS is 15 over 17 divided by root 2, right? Then from here, okay, let me try to erase some, right? So I'm having what? P average equals to what here? VRMS, okay, times IRMS, which is 15 here. Here it's 17 over what? Over root 2. Then multiplied by what? IRMS. Okay? IRMS. Then my IRMS will be what? It will be 15 over 17 divided by what? By root 2. That will be my what? IRMS. Learners, we are not supposed to round off this answer, right? Because this is not your final what? Final answer, right? Then now I have IRMS. I know IRMS is given by what? By I max divide that by what? By root 2. What is my IRMS? It should be 15 over 17 divided by root 2, and then equals to I max, right? Divide by what? By root 2. Then I need to multiply by root 2, multiply by root 2. So when I multiply this by root 2, it's when I will get my I what? My I max. Then you just need your calculator there. Then you get your answer in what? In amperes. So it's not something that is difficult. All right. So check. This is not a difficult topic, learners. But please, even if it's not difficult, spend some time here because you need to get all these marks. Yes, we understand it carries a few marks, but we need those few marks to pass. All right. So let's look at 9.3. Draw a graph of current versus time for the same time period as the above graph. Indicate the values of Imax and IRMS on the graph. So the shape will be the same. The shape will be the same. So the shape, same shape. right? So it will be the same shape, right? Then there you have what? The maximum. Even here you have the maximum. And what is the maximum? Maximum is 1.77. And then the root mean square, current is 1.25. So it's what they wanted us to indicate. Okay, so where am I getting these values from? Our calculations, learners. All right, so same shape, right? But the difference will be that on your vertical axis you are having current now in amperes, and when on your horizontal axis is still time in seconds. So the shape will be the same, but now the values will be different because we are no longer talking about what the root mean square, voltage, maximum voltage, but they're talking about what IRMS and what an IMAX. So that is very, very important, learners. All right, let's move to another question because we still have time. So the diagram shows a simple electric motor. It's a motor. So it converts electrical energy to mechanical energy. It's based on which principle? Motor effect, right? So is it an AC or a DC? So we need to check the components. So, okay, I can see that component there. This is what? A split ring. It's a split ring commutator. So it's a split ring commutator. So, okay, this is a motor. What is the function of a split ring commutator? Motor is about rotation of the coil. Okay, this is a split ring commutator. So it ensures that the coil rotates in one direction. All right. So that is the function of split ring commutator when it comes to a DC. This is a DC motor. Why DC? Because of that split ring commutator. All right. And you can see, let's say you didn't read this statement. You ignored this statement and you don't see a source of power. You are going to say this is a DC generator. That is why I said to you, please make sure that you read the statement given and then before you answer the questions. Okay, so you need to read, learners. What energy conversion takes place in electric motors? You can't say there's no energy, right? The energy conversion, we know it's always for motors is from what? Electrical to what? To mechanical. All right, then 9.2. What type of electric motor, AC or DC, is illustrated in this diagram? You have to choose. It can't be both, right? It's either AC or DC. In this case, because I see there's a split ring commutator there, then this would be a DC. Then I get a mark there. All right. This is a DC. Give a reason. You can't say it's because I can see it is a DC. No. Give us a reason why it is a DC. The reason is because it contains what? Or it consists of what? It consists of a what? A split ring commutator. Right. It consists of a split ring commutator. So that's the reason why it is a DC motor. It consists of what? Of a split ring commutator. Then you'll get another mark. So now we have how many marks? 3. 9.1, straightforward. 1 mark. 9.2, 2 marks. Also straightforward. Okay. As long as you know your story. Then explain the function of the carbon brushes. Carbon brushes, what is the function of it? They make contact. Remember, this is what now? This is a motor. So they make contact with this split ring with the splitting commutator to ensure that current reaches the internal circuit. Right? So that is the function of the brushes. So they make contact with the split ring commutator to ensure that the current also reaches the internal circuit or the coil. All right. To which terminal, right? That is your 9.4. To which terminal of the power source, positive or negative, is the brush labeled P connected if the coil rotates clockwise? To which terminal of the power source, right? Positive or negative, is the brush labeled P connected if the coil rotates clockwise? Okay, let's go back. Let's go back. Right, so the brush label P is this one. See, it's this one. And we are told that the coil rotates clockwise. Okay, if the coil rotates clockwise, this part will move down and then this part will move up. This side of the coil, where you have south pole, it will move down. And then this side of the coil, where you're having north pole, it will move up. So it will be up, down, and that will show what a clockwise what movement or rotation. All right. So then we want to check, okay, whether P is positive or what, or negative. Is it connected to the positive terminal of the battery or negative terminal of what, of the battery? All right. So let's check. So this is a motor, learners. So for motors, we are using left hand rule or Fleming's left hand rule. So I'm using my left hand, right? So check, index finger is pointing south, correct? Then check, the thumb is facing up. So I'm checking this side. I will just say this is side AB. So I'm checking side AB, whether side AB, the current will be A to B or from B to A. All right? So let's start there. Index finger pointing south, north to what? To south. Then the thumb is facing up, and that is correct. I'm checking side AB, learners. All right? So the thumb is facing up, and if the thumb is facing up, that is correct. The force is up because side AB will move up. Then the current should be out. If I'm saying the current should be out, it is from what? From B to what? To A. So it will be from B to A, and then this side, it should be like this. So the current is in this side, but on the other side where you have AB, it is what? Out. Is from B to what? To A. Then what about the terminals now? Right. So with the terminals, remember current always flows from what? From the positive terminal to what? To the negative terminal, conventional. All right. So it's from positive to what? To negative. So from positive, so which means that this would be what? Positive, right? Positive to what? To negative. So this is negative, this is positive. So it's from positive terminal to what? To negative what? Terminal. So here it will be what? It will be negative. So where brush P is connected, then it will be connected to the negative terminal of what? Of the battery. So I'm using left, all right? I'm using left because this is a motor, north to south. Side AB will move up. Why? Up because we are told that the coil rotates clockwise. So if the coil rotates clockwise, side AB will move up. So if side AB moves up, then the current is out, which is A to, which is B to what? To A. So B to A, this side it will be what? A to B. So this side, where the current is in, is positive. Where the current is out, it will be what? Negative. Because current flows from what? From positive terminal to what? To negative terminal. All right. So P would be what? Would be negative. All right. So let's check 9.5. 9.5, name and explain the basic principle on which a motor works. Right. So name, right? We are naming the principle. Motor what? Effect. Okay. Motor effect, the coil. Now I'm explaining. The coil experiences two magnetic fields. Why am I saying it experiences two magnetic fields? Remember, there is magnetic field due to the magnets, right? So there's also magnetic field due to current in a coil, right? So as long as there's current in a coil, around that coil, there will be what? A magnetic field. So this coil experiences how many magnetic fields? Two. So the coil experiences what? Two magnetic what? Fields. So since it experiences two magnetic fields, the coil will start to do what? To rotate. So I've explained motor effect. The coil experiences two magnetic fields. So since it experiences two magnetic fields, then a force will be created, right? Then it will start to do what? To rotate. Okay, so that is motor effect. So name of the principle is motor effect, and then I'm explaining motor effect. The coil will experience a magnetic field due to the magnet. It will experience another magnetic field due to the current in a coil, And then since this experiences two what magnetic fields, then the coil will start to do what? To rotate. Then you have what all the marks there, that 2 marks. So let's look at the last question. An electrical appliance with a power rating 2000 watts, right, is connected to a 230 root mean square household mains what supply, right? So an electrical appliance with a power rating of 2000 watts is connected to a 230 root mean square voltage household main supply. Calculate. So before that, let's understand what is going on here. Sometimes instead of giving, fortunately here you're given that 230 is root mean square what voltage. Sometimes they will say the electrical appliance is labeled as follows: 2000 watts and 230 watts, 230 volts. They won't even tell you that 230 volts is what is it the root mean square voltage or the maximum voltage? But you should know it's always what the root mean square what the root mean square what voltage. Okay, so that is the root mean square voltage. So you're given two things: the power and the root mean square what voltage. So they want the peak voltage. Peak voltage, that is the maximum voltage. All right. So how are we going to get the peak voltage given the root mean square voltage? All right. So we want the peak voltage. Peak voltage, it's the maximum what voltage. The equation Vrms equals to what here? Vmax over what? Over root 2. So root mean square is 230. So you can see what I've done here. I've copied the equation as it is, and I didn't manipulate it. I know that I'm looking for Vmax, but there's no need for me to write the manipulated what equation. No marks for manipulated equations, learners, right? And I think it's better this way. Remember, when it comes to physical sciences, right, physics, we give marks for the correct equation, right? Not for the manipulated equation. For the correct equation, we give a mark for correct substitution. We also give a mark for what? For the correct answer with the units. All right. So correct what equation? Copy it as it is from the data sheet, right? Then substitution. This is Vmax. It's what I'm looking for. So divide by the root 2. Then here it will be Vmax. Then I will get the answer, which is 230 times what? Times root 2. Then I will get my answer in what? In volts. So it will be what? Vmax, Vrms equals to Vmax over root 2. You get a mark for that, a mark for correct substitution, a mark for correct answer with what? With units. Then you'll get how many marks there? 3 marks. All right. So let's look at 9.6.2. The root mean square current passing through the appliance, also 3 marks. They want the root mean square what? Current. Okay, so I need the root mean square current. There are so many equations that I can use to calculate the root mean square what? Current, right? So root mean square current, I have P average equals to what? Vrms, Irms. Okay. I also have P, not the other one, I can't use it because there's R, where you have P average equals to V squared RMS over R, and P average equals to I squared RMS times R. I can't use that one because I don't have the resistance. But another one, it will be what? I RMS equals to I max over what? Over root 2. So if I want to use this one, can you see that I will have two unknowns? I don't have root mean square current. I don't have what? Maximum what? Current. So I can't use that one. Okay. So rather, I have to use the first one. So when I'm using the first one, it will be P average, because I'm giving the average power, equals to V RMS multiply that by R RMS. All right. So average power 2000, and then V RMS already we are given the Vrms, which is 230. You multiply that by what? By root mean square what? Current. Then root mean square current will get your answer in what? In amperes. Then you also get how many marks there? 3 marks. A correct equation, it's a mark. Correct substitution, correct answer with what? With units. Then you get how many what? How many marks? 3 marks. Right. So let's look at the last one. Okay. Right. The resistance of the appliance. They want the resistance. There are only 2 equations when it comes to your data sheet where you have resistance. All right. There are only 2 where you have what? resistance. Okay? Where you have resistance is this one, is P average equals to I squared RMS times R. There's another one, average power equals to V squared RMS over what? Over R. So there are two. So it's up to you, because now we have everything. All right? So average power 2000. All right? Equals to I squared RMS. I squared RMS, the answer that you got there, squared, you multiply that by what? By R. So the previous answer, even if it's wrong, there's what we call positive marking. Use that answer. That is why you need to have confidence in your answers, because you don't even know whether they are wrong or right. So you must have confidence in your answers. Second, let me just check which question is this. 9.6.2. You were asked to calculate what the root mean square current. So if your root mean square current is 1000, it's still fine. You won't get a mark for that 9.6.2. But if you're going to use that 1000, that 1000 here, then you'll get all the marks. There is what we call positive marking, learners. So you need to have confidence in what? In your answers. So your answer in 9.6.2, you use it here, then you'll get your R in what? In ohms. So it's still fine. A correct equation, correct what? Substitution, correct answer with what? With units. Then here, root mean square, voltage 230 squared. And learners, you have, I don't know why you always forget a square, especially when it comes to substitution. You do this when it comes to your momentum and impulse, where you have to prove whether the collision is elastic or inelastic using the equation EK half mv squared. You'll write the equation correctly, EK equals to half mv squared. Then when it comes to substitution, you forget that square. You will lose marks for doing that. Even when it comes to such equations where there's a square, you always forget to put a square. If you are going to forget to put a square, no marks for substitution. All right? So please, learners, relax and make sure that you do everything the way it's supposed to be. All right? So make sure that when it comes to substitution, when you see that square, for example, here, you can see it's V squared. It's not just V. So if you're going to write 230 divided by R, it's wrong. It's supposed to be 230 squared. You divide that by what? By R. And what is your average power? 2000. Then you'll get your R in what? In ohms. Okay. A mark for correct equation, a mark for correct substitution, and a mark for correct answer with what? With units. So that was our last question, learners, right? So that is your electrodynamics, your question 9. It's not a difficult question. We are expecting you to get all those marks. It's not difficult. You have seen that, and you have seen how easy questions are. But sometimes these questions, they need your thinking. For example, I was looking at that question where you were supposed to find the DC voltage. So if you don't know that the DC voltage is equivalent to what? To root mean square voltage, then you are going to have what? A problem. So sometimes some questions, they need your thinking, but not a lot of thinking. So please, learners, make sure that you collect all the marks when it comes to electrodynamics. So we have come to the end of our lesson, learners. I hope you gained something. You gained something, and you are going to make us proud. Come the 11th of November, you will do it. Thank you very much. Enjoy the rest of the day. Bye-bye.